Hi everyone, let's work on a trough problem. So this in some ways is kind of like the swimming pool problem, and I know this is a type of problem that can be tough for people just on the setup, so I like to do a couple variations on this. So I have a water trough, and it is 10 feet long, and I'm going to assume that the shape of the trough is not changing. The vertical ends of the trough are isosceles triangles, so two sides are equal. They are 4 feet across the top. This is not looking good for my scale at all. And the slopey side is 3 feet, both slopey sides. Okay, so this sort of, okay, so this trough has cross sections that are isosceles triangles. So we have water flowing into the trough at a rate of 2 cubic feet per minute. And we want to find the rate of change of the depth of the water when it's 1.5 feet deep. So this 2 cubic feet per minute, that's the volume. So I'm going to call that dV dt. Volume, and you want to be really clear, this is the volume of the water, not the volume of the tank. So the water is sitting in here somewhere. It's not all the way full, and we're interested in that volume. Okay, we want to find the rate of change of depth, so I'm going to, here, let's change it up. Call that y. We want dy dt when y is equal to 1.5 feet. Okay, so we need a formula that relates the volume of the water to its depth y. So this again is a prism. This is a triangular prism. These prism shapes where it's some fairly straightforward two-dimensional shape and you are trying to stretch it out and make it three-dimensional, it's always going to be that area of the base multiplied by the height of the shape. So the base is a triangle. The area of a triangle is 1/2 base times height, and then the length of this whole thing is 10. So this is my, I'm going to call that my, y. Here, let's go back in here. I didn't call it h this time. I called it y, and then this is my b. So I have 5by, which is all fine and good, but I don't have any information about b, and I'm not interested in b. So I need to figure out how to eliminate it. So we should see sort of a common thing arising here. We have similar triangles. But I didn't make this one super easy on us. So here's our similar triangles. So we could say, for the little triangle, if we're trying to get rid of b, we could say the ratio of b to h is equal to the base of the big triangle, 4. But here's where we run into a little bit of trouble. We don't actually know the height of the big triangle. We know the slanty sides. So we're going to have to do side work for our side work here. I promise the ones I gave you in your homework aren't quite so bad. I did the messy one for you in the video. So if we look at this big triangle and we cut it in half, we have a side length 2 and a side length 3, and we're looking for, here we'll call this one h. So you can use a Pythagorean theorem to find that. You could use trig functions to find that, I'm sure. So I'm just going to say 3 squared is 9 equals 2 squared, 4 plus h squared. So 9 minus 4 is 5. The square root of 5 is going to be my height. Okay, so this is root 5. Okay, which means that b is equal to 4 over root 5h. Okay, so volume 1/2 4 over root 5h. Oh, h. Did I do it again? b over h. Yes, it's not an h, it's a y. This is why I should just stick with my habit of calling it h and not get all these variables mixed up. Okay. And I can even do a little better than that, so I can cancel a 2, and oops, I get 2 over root 5 y squared, in case anyone doesn't know why I just threw that in. The b got replaced with 4 over root 5 times y. This y should still be sitting there as well. Okay, so dv dt, taking the derivative of this, we're going to have a power rule, so it'll be a 4 over root 5 again, y, and then a dy dt. So we're looking for this dy dt. We know the dv dt is 2, and we know the y is 1.5. This is silly because you can just plug it into a calculator, but I'm going to make it 3/2 so that I can cancel out a 2. Okay, so I have 6 over root 5, and if I want to get rid of that, I need to multiply by root 5 over 6. So I get dy dt is root 5 over 3. Again, I'd be completely happy with the decimal there. Go ahead and switch if you'd like to. I think it's nice to check and see how reasonable these things seem to be. Root 5 is a little bigger than 2, so this is a little bigger than 2/3. And the units, this is depth, should be feet per minute. So the depth of the water at that point in time is increasing by a little bit more than 2/3 of a foot per minute. Notice that this absolutely will change depending on whether you're near the bottom or the top. Near the top of the trough, since the water is still pouring in at the same rate, it's going to be slower. Near the bottom of the top, it's going to be quicker. All right, thanks for watching.